Welcome you all to physics class after Diwali. Very good morning to all of you. In this class today, we are going to first talk about work and power in rotation. We will also prove the kinetic energy theorem for rotation. We are doing rotation for quite some chapters or quite for large number of lectures. So if you need a revision, please go through the video numbers 48, 49, 50, 51, 52, 53, etc. So how do we define work? We know that we define work as force into displacement. Can we have an equivalent definition for rotation? Answer is yes. Let us have a rigid body which is rotating about some point O. The axis of rotation passes through the point O and it is perpendicular to the screen. Now take a point in the rigid body which is at distance r from point O or distance r from the axis of rotation. And let us say that some tangential force works on that point which is F tan. This tangential force will induce rotation. As a result, in a very small time interval dt, the point and hence therefore the body rotates by an amount d theta. In the meantime, the displacement of this particle will be a small infinitesimal displacement ds. Now I can correlate these quantities. Work done by the force is force into displacement. That is F tan is my force and ds is my displacement. So the work done is F tan into ds. You can see that they are in the same direction. So I don't have to worry about angle between them. But the geometry tells us that ds is equal to r d theta. The definition of d theta is ds upon r. So ds is equal to r times d theta. So I can use this fact in this. So I will get dw is equal to f tan r d theta. Now f tan into r is nothing but the torque acting on the body. So if you have to calculate torque of f tan about the point O, then we have seen how to calculate torque. It is the f tan into perpendicular distance from the point to the line of action of force, which is r in this case. Therefore, r into f tan will give me the torque. Therefore, this equation can be written as dw is equal to torque tau into d theta. So you can see that this will replace the formula for work done in rotation. In linear motion, the work done is F into ds. In rotation, force is replaced by torque and displacement, linear displacement is replaced by angular displacement. So dw is equal to torque into d theta. If you want to total work done, then you simply have to integrate this over all the particles of the rigid body. So that's not a big task. So total work done is integration, or if you want to get the total work done from theta 1 to theta 2, starting from one angle and ending at one angle, then your limit of integration can be theta 1 to theta 2 tau d theta. That will give you the total work done. If the torque is constant, then it will come out of the integration sign. and integral of d theta will give you simply theta. When you apply the two limits, it will be theta 2 minus theta 1, which can just be written as delta theta. So if the torque is constant, then the work done is tau delta theta. So that was the work done in rotation. Now let's prove the work kinetic energy theorem in rotation. That's very straightforward. We have already achieved this integral in the last slide. All I can do is I can replace torque by I times alpha, where I is moment of inertia and alpha is angular acceleration. And I assume that I is constant. I will take it out from the integral. Alpha is angular acceleration, which can be written as rate of change of angular velocity, d omega by dt. And then I can interchange d omega and d theta. So it will become d theta by dt into d omega. D theta by dt itself is nothing but omega. So I will get an omega here. And then I can carry on the integral. Integral of omega is omega square upon 2. And if you put the limits omega 2 and omega 1, you get total work done. Half I is equal to half I omega 2 square minus half I omega 1 square. Now what does it say? If you look at this term, this is nothing but the rotational kinetic energy of the body. So all it is saying is that if the work is being done by a torque on a rotating body, the rotational kinetic energy changes. And the change in the rotational kinetic energy is equal to the work done by the torque. So that is the work kinetic energy theorem in rotation. The change in the rotational kinetic energy of a rigid body equals the work done by the forces exerted from outside the body. Remember, all inside forces and all inside torques will cancel out each other due to Newton's third law. So they don't figure out anywhere in the picture. How about power? Now, how do we define power? So we define power by rate of work done or rate at which the work is done. So if work done dW is tau into d theta, then the power P is dW by dt, which can be written as tau into d theta by dt. But d theta by dt, as we all know, is angular velocity, omega. And therefore power is tau omega. It is very similar to the equation for power in translational motion, where it was Fv. So again, tau replaces the force, omega replaces v. We stop here in this class. Next class we are going to talk about gyroscope.